Today I'll be explaining the concept of truth table as part of chapter 2 in MAT222. A truth table is used to display the relationship between the true value of proposition. First, let's see the truth table for negation. You have to negate the true value of the proposition. For example, if P is true, then the negation P is false and vice versa. Next, truth table for conjunction. P and Q is a proposition that is true when both P and Q are true and false otherwise. Then, truth table for disjunction is when P or Q is the proposition that is false when both P and Q are false and true otherwise. Next, the truth table for implication is when P implies Q is the proposition that is false when P is true and Q is false and true otherwise. Then, the truth table for biconditional statement. P logically implies Q is the proposition that is true when P and Q have the same true value and false otherwise. Okay, now let's look at the first example question. Show that P implies P or Q is a tautology by using truth table. Tautology is a compound proposition that is always true. As you can see, this is how to solve these questions by using truth table. Now let's move to the next questions. By using truth table, prove that P and Q logically implies P if and only if Q. This is how we're gonna solve the questions. Now, for the last questions, P or Q and negation R. Here how it looks in a truth table.
Next, we will talk about the laws of logic.
In laws of logic, we have PQR as primitive proposition, capital T as tautology, and capital F as contradiction.
First, we have double negation law. If we have not P equal to P, and if P is true, then not P is false. So if we have not P, it is equal to P, which is true. Second, we have De Morgan's law. Negative P or Q equal to negative P and negative Q. Next, negative P and Q equal to negative P or negative Q. Next, we have commutative law. P or Q equal to Q or P, and P and Q equal to Q and P. Next, we have associative law. P or in bracket Q or R equal to P or Q in bracket or R. And we have P and Q and R in bracket equal to P and Q in bracket and R. Next, we have distributive law. P or in bracket Q and R equal to, we expand it into P or Q in bracket and P or R in bracket. Next, P and Q or R in bracket equal to P and Q in bracket or P and R in bracket. For idempotent law, we have P or P equal to P and P equal to P. Next, inverse law. P or negative P equal to T, which is tautology, and P and negative P equal to F, contradiction. Next, we have identity law. P and true equal to P, and P or false equal to P. Next, we have domination law. P and false equal to false, P or true equal to true. If at least the compound proposition is true, then the whole is true. Next, we have absorption law. P or P and Q in bracket equal to P. P and P or Q in bracket equal to P. It is like distributive law, but they have 3 propositions, and the absorption law only have 2 propositions, which is P and Q. Next, we have definition of implication. P implies to Q equal to negative P or Q. We change the proposition P into negative P, and we change the implied symbol to OR symbol. Next, we have definition of biconditional. We have P biconditional Q equal to, we expand it into P implies to Q in bracket and Q implies to P in bracket.
Now we have example question. Let's solve it together. For example 1, show that the following expression is a tautology by using the laws of logic. First step is equivalence identity. We change the implied symbol to OR symbol. Second step is absorption law. Third step, we use De Morgan's law. We expand the negation symbol and we change the AND symbol to OR symbol. Next is associative law. We change the position of bracket while all the symbol is the same, which is OR. Next, commutative law. We change the position between R and P. Next, associative law again. We change the position of bracket. Next, idempotent law. We simplify P or P equal to P. Next, inverse law. We simplify negation R or R equal to T, which is tautology. Last step is domination law. We simplify P or T equal to T, tautology. So that's the final answer for example 1. Next, example 2. Simplify the following expression. First step, we use definition of biconditional. Second step, we use commutative law. We change the position of Q and P. Next, associative law. We change the position of bracket. Next, we use absorption law. And the last step is definition of biconditional again. We simplify from Q implies P and P implies Q into P biconditional to Q. So that's how we simplify the following expression for example 2. For example 3, simplify the following expression. First step, identity law. We change P equal to P and true. Next, distributive law. We simplify it into P and T or Q. Next, domination law. T or Q equal to T. Last step, identity law. P and T equal to P. That's how we simplify example 3. So the conclusion is, in mathematical logic and proving techniques, the laws of logic are the basic rules that ensure clear and correct reasoning. They help us create and verify proofs by showing whether statements are true or false. These laws are the foundation for methods like direct proofs, proofs by contradiction, and induction, making them essential for solving mathematical problems.
Hi everyone. Okay, so I'll continue this video with my topic, which is rules of inference and argument. Okay, so argument. Argument is a list of given statements called premises, followed by the final statement that we call as conclusion of the argument. Okay, so as you can see, P1, P2 until Pn is a premises that can be called as hypothesis, and Q is a conclusion. So this is an example for argument in symbolic logic. So the two statements above are premises, while negation P below is a conclusion. First, we rewrite the premises given and label it as a premises. Then, we can start to answer the question. So from 2, we can use simplification rules that can only be used for conjunction statement that says two things are true together and that allow you to choose one of them. So we choose negation Q. Then from the first premises, we use definition of implication rule to change the form of implication. Next, we use distributive law to factorize the previous step. Then we got negation P or Q by using simplification rules as we have conjunction symbol. And lastly, from 3 and 6, we use rules of disjunctive syllogism. Basically, this rule is similar with modus ponens, which means that we have negation P or Q and negation Q is true, then we can conclude that negation P is true. So the argument is valid. But remember, modus ponens can be used only for implication statement, while disjunctive syllogism is for disjunction statement. Okay, so next subtopic that I'll be explaining is about rules of inference. So, truth table, law of logic, and rules of inference is 3 ways that we can use to find the validity of an argument. So, as we know, truth table is not really practical to determine the validity of an argument involving more than 3 propositions because the number of rows will be too much. So, in order to avoid large truth table, we can use rules of inference. We have 8 types of rules that we usually use, which is modus ponens, modus tollens, law of syllogism, addition, simplification, contradiction, rule of conjunction, rule of disjunctive, syllogism. Okay, let's do 2 examples of question. First, to solve an argument that was given in paragraph, we need to find and label the premises with an alphabet. Next, to change implication statement from the first premises, we use definition of implication law. Then, we expand the statement using distributive law that we learned in topic law of logic. Next, as we got conjunction statement, I decided to choose negation P or Q using simplification rules, and again, I choose negation Q by using simplification rules from the second premises. Then, we can use rule of disjunctive syllogism. So this argument is valid as we got P as the answer. Last example, first step, I use law of syllogism rule. So this rule is applied when there are 2 premises in the form of implication, where the hypotheses of the first premises are the same with the conclusion of the second premises. Therefore, we can eliminate it and combine the remaining variable together. So from third and fourth premises, we got negation R implies P. Then, we got negation P by using simplification rules from the first premises. Next, we use modus tollens from 2 and 6. So basically, modus tollens is the opposite of modus ponens. In simpler way to explain modus tollens, if we have the first statement P implies Q is true, and the second statement negation Q tell us that Q is false, then we can conclude that P must also be false. So this argument is valid as we got P as the answer. In conclusion, an argument is said to be valid if and only if, in every case where all the premises are true, the conclusion is true. Otherwise, the argument is invalid. So to validate an argument, rules of inference is the simplest and effective method. That's all from me. I'll pass it to the next presenter.
Today, in Chapter 3, we will talk about forward-backward method.
For introduction, first we need to recognize which one is hypothesis and conclusion from the statement. Then, to prove A implies B, we have to assume that statement A is true and use any information so that B is true. There are 2 processes involved in this method. First, backward process. When writing to prove to reach the conclusion that B is true. This step is when we want to find B1 by asking key question repeatedly until it can't be answered anymore. Then, move to forward process. Derive from statement A to get other statement which is A1, A2 and so on, so that it can link up with the last statement from the backward process. Now, we will look at some example. First, if the rectangle XYZ is side of length X and Y and hypotenuse of length Z has an area of Z squared over 4, then the triangle XYZ is isosceles. In this solution, statement A will be if the rectangle XYZ with side of length X and Y and hypotenuse of length Z has an area of Z squared over 4, then statement B will be the triangle XYZ is isosceles. In backward process, we write it as X equal to Y. Is it because isosceles triangle have 2 equal length of side? Then in backward process statement 2, we write it as X minus Y equal to 0. It is because we have to prove that X and Y have the same real number. Then we proceed to forward process. In forward process, we write 1 over 2 xy equal to z squared over 4. It is area of triangle. Then move to x squared plus y squared equal to z squared. It is by Pythagoras. Then we substitute z squared equal to x squared plus y squared and do some algebra to get x minus y equal to 0. Then is it proven that statement A6 equivalence with statement B2. Next, we move to condensed proof. Condensed proof is solution, but we write it in sentence. For example, from the hypothesis and formula for the area of triangle, the area of xyz equal to xy over 2 equal to z squared over 4. By using the Pythagoras, x squared plus y squared equal to z squared, on substitute z squared with x squared plus y squared and performing some algebraic manipulation, we obtain x minus y squared equal to 0. Hence, x is equal to y and the triangle xyz is isosceles. Second example, if p is an odd integer, then p squared is an odd integer. For this solution, statement A is p is an odd integer, while statement B is p squared is an odd integer. For backward process, p squared equal to 2k plus 1 for some integer k. This is according to the meaning of odd integer. Then we move to forward process. P equal to 2n plus 1. Is this because of the meaning of odd integer also? Then move to, we square on the both side and we get 4n squared plus 4n plus 1. Then we factoring it with 2 and we get 2 bracket 2n squared plus 2n plus 1. Then let k equal to 2n squared plus 2n. Then we get 2k plus 1. Then is it proven that A2 equivalence with statement B1? In this condensed proof, from the hypothesis, p is an odd integer. By the definition of odd integer, p equal to 2n plus 1. Squaring the left side of p equal to 2n plus 1, we get p squared equal to 4n squared plus 4n plus 1. Factoring 2 and we get 2 bracket 2n squared plus 2n plus 1. And this will equal to 2k plus 1, where k equal to 2n squared plus 2n. Thus, p squared equal to 2k plus 1 for some integer k, and p squared is an odd integer. Last example. If triangle ABC is equilateral, then the area is square root of 3 over 4 times the square of the length of a side. In this solution, statement A is triangle ABC is equilateral, while statement B is the area is square root of 3 over 4 times the square of the length of side. In backward process, we get area of triangle equal to square root of 3 over 4 times x squared. We get this area from here. In forward process, area of triangle equal to 1 over 2 multiplied by base and height. And we using Pythagoras to find h. Then we get square root of 3 over 2 and times with x. Then we use all the information and put it into the formula of triangle and we get square root of 3 over 4 times with x squared. And it is proven that statement A4 equivalence with statement B1. For this condensed proof, from the hypothesis and formula for the area of triangle, the area of ABC equal to 1 over 2 multiplied by base and height. By using the Pythagoras, then x squared equal to s over 2 squared plus h squared. And performing some algebra manipulation, we obtain h equal to square root of 3 over 2 x. Hence, the area of triangle ABC equal to square root of 3 over 4 times with x squared, and the area is square root of 3 over 4 times the square of the length of a side. Proceed to the next topic. I will explaining about mathematical induction. What is mathematical induction? Mathematical induction is a method for proving that statement Pn is true for every natural number, which is n, so that we can solve indefinitely cases such as P0, P1, P2, P3, and so on. This method is done by proving a simple case by showing that if we assume the first claim is true for the given case, the next case is also proven to be true. For the concept of mathematical induction, we need to use 3 steps. To solve this question, first, we need to extract the information from the question itself, where n squared is bigger than or equal to 2n, where n is an integer, and n is bigger than or equal to 2. The Pn that we can build is Pn equals to n squared bigger than or equal to 2n, where n is bigger than or equal to 2. By following the 3 steps of concept of mathematical induction, the first is show that P1 is true. But for this answer, the first sequence of our question is 2 because n is bigger or equal to 2. So P2 equals to 2 squared is bigger than or equal to 2 times 2, where 4 is bigger than or equal to 4, which is proven to be true. For the second step, assume that Pn is true, where our Pn is Pn equals to n squared is bigger than or equal to 2n for all integers where n is bigger than or equal to 2. For the last step, show that Pn plus 1 is true. How? We need to substitute n plus 1 into n from the equation Pn. So, the equation for this is, in bracket, n plus 1 squared is bigger than or equal to 2 times n plus 1. When we solve this equation, we get n squared is bigger than or equal to 1, where n is bigger than or equal to 2. Thus, 2 squared is equal to 4 bigger than or equal to 1. Then, p n plus 1 is proven to be true. For the second question, the information that we can extract from this question is n is an integer, where n is bigger than or equal to 1. The Pn is sum of k times k factorial, where k start with 1 is equal to, in bracket, n plus 1 factorial minus 1. The first step show that P1 is true. For this question, we need to compare left-hand side and right-hand side, where left-hand side is P1 equals to sum of k times k factorial, where we get the answer is 1. For the right-hand side, P1 is equal to 1 plus 1 in bracket factorial minus 1, where the answer is also 1. When we look at the answer for the left-hand side and right-hand side, the answer is the same, where 1 equals to 1. Then P1 is proven to be true. Second step, assume that Pn is true, where Pn is equal to summation of k times k factorial equals to, in bracket, n plus 1 factorial minus 1. For the third step, show that Pn plus 1 is true. As we solve the first step, we use left-hand side and right-hand side. For this step, is also the same. So for the right-hand side, we substitute n plus 1 into n. So it becomes, in bracket, n plus 1 factorial minus 1, where the answer is, in bracket, n plus 2 factorial minus 1. For the left-hand side, we need to use Pn plus n plus 1. Remember, Pn plus n plus 1. Then, we substitute all the n plus 1 into the equation, and then we also get, in bracket, n plus 2 factorial minus 1. Thus, left-hand side is equal to right-hand side, which can show that Pn plus 1 is proven to be true. For the last example, the information that we can extract is Pn equals to multiplication of 1 minus 1 over I squared, where I begin with 2. Is equal to n plus 1 over 2n. For the first step, show that P2 is true. Why 2? Because for this question, I start with 2. And for this question, we also use left-hand side equals to right-hand side. We need to compare left-hand side and right-hand side. For the left-hand side, P2 equals to multiplication of 1 minus 1 over 2 squared, where 1 minus 1 over 4 becomes 3 over 4. For the right-hand side, P2 is equal to 2 plus 1 over 2 times 2, where the answer is also 3 over 4. Then, P2 is proven to be true. For the second step, assume that Pn is true, where Pn equals to multiplication of 1 minus 1 over I squared equals to n plus 1 over 2n. And then the last step, the third step, we also need to show that Pn plus 1 is true, by using comparison between right-hand side and left-hand side. For the right-hand side, Pn plus 1 equals to n plus 1 over 2 times n plus 1, where the answer is n plus 2 over 2n plus 2. For the left-hand side, for the previous question, we used Pn plus n plus 1. But for this question, because it using multiplication, so we need to use Pn times n plus 1 squared, where the answer is also n plus 2 over 2n plus 2. So, now, the left-hand side is equal to right-hand side. Then, Pn plus 1 is also proven to be true. That's all.